A very good day to all of you. What's in store for today's learning idea? The article in the front of you is a capacitor. So we are going to learn capacitor with me. And what is a capacitor? What's the feature of it? What's the insight of a capacitor? Where do we use it? What's the commercial uses of it? What's the practical use of it? And what basic purpose does it serve in our daily life? These questions are going to be answered in a few while. Not all of them are going to be answered in today's lecture, but certainly you will get some knowledge deeper into the term of the capacitor. So let's enter into the capacitor world. So first of all, the visual effect. That what do you see as a capacitor? We see as a capacitor as a structure of different kinds. Was the first impression of a capacitor. These days, the first impression is created by the Google, by getting into the Google images. So type a capacitor over there and what pops up, you will popping up seeing a cylindrical capacitor. That means a cylindrically shaped capacitor, just like this on the image, which you are able to see. This is like a cylindrically shaped capacitor. Does that mean that this is the only size shaped capacitor? It's not like that. There are other different kind of the capacitors also. What different kinds, what different shapes, as you can see up on the screen. And what do they are featured and said to be termed as. This capacitor is labeled as a spherical capacitor. Why it's supposed to be a spherical capacitor? In the terminology, reason because the plates, repeating once again, the plates of this capacitor are spherical in shape. These are like concentric spheres. This is like a cross section of it shown to you. The inner plate having a positive charge, the outer plate having a negative charge, which confines the electric field between them. And the electric field is what? It's a visual effect on our minds to explain to us the idea of the electrostatic potential energy stored in this region. Towards the left side, which you visualize, is supposed to be a cylindrical capacitor. What's the difference and what's the similarity? These both capacitors have the similarity as the twin plates. Both of them have two plates, one of which is carrying a positive charge, the second carrying a negative charge. That's a similarity. And the reason for such behavior is to confine the electric field lines between the plates. What's the difference between them? As you can see, the structure, the size, the shape. In the spherical capacitor, we are dealing with the concentric spheres. In the case of the cylindrical capacitor, we are dealing with the coaxial cylinders. What's on the right side, which you can see the image? This is like a motor capacitor. You can see this kind of a capacitor fitted into your motor as a starter capacitor. It is used for starting that particular motor. The most common kind of a capacitor which you can see around you. What's a capacitor? So let's slow down and answer in brief that what is a capacitor? A capacitor is basically a modified conductor which accumulates the charges, a huge amount of charges on its plates. And extra, it also encloses the associated electrostatic potential energy. Let me mention for you that what is a capacitor. So the answer for what is a capacitor is, a capacitor is a modified conductor. That means it is an arrangement of conductors which accumulates the charges on its plates. The plates in this article of electromagnetism is supposed to be by default termed as conducting plates. So charge on its plates and also the associated electrostatic potential energy between the plates. That's the prime article actually. What's the prime article? That it basically uses the electrostatic potential energy stored between the plates. Now, do this hint up like this behaves like a battery? No, a battery and a capacitor, there are two different things. There is a similarity. that both of them are taken as the prime sources of energy, but they're different in many aspects. That difference will be told to you through the study of the lecture. So both of them are basically sources of energy. That means you can store the energy between them, between their terminals or between the plates, and as and when required, you can retrieve the energy. You can take back the energy. In a capacitor, there is a feature where you can use that energy in a slow mechanism, in a slow mannerism, and such kind of behaviors will be known as transient behavior. And the circuits which will be designed on the basis of that to retrieve the energy in a slow phased manner will be defined as a transient circuits. And if you want the energy to be quick, just like this, just like the flash of a camera, if you want the energy to be like that, in that condition, you require instantaneous release of energy. And the circuits which will be designed on the basis of that will be termed as an instantaneous circuits. Another question which hits my mind very often is a capacitor a DC device or an AC device? So I say it's both, has a different behavior for DC. What kind of behavior? To just mention in a short note, it blocks the DC. When it is high on potential, when it's in the steady state, it blocks the DC. But it has a different altogether behavior in AC. The DC means a direct current, AC means alternating current. In our household, we get a supply of the alternating current. There, the capacitor has a different behavior. It behaves as a filter. We will, of course, study these things in very much finer details. Now, what are the factors which affect the capacitance? So we're talking about conductors in detail. The same conductor, which is made up of copper, can have varied properties. Like we say the three alphabets. How many? The three alphabets of the electrical circuits as a L, C, and R. R is a resistance, which you have studied in detail. You know that practically. There are two other aspects of it. That's the capacitance and the inductance. The capacitance is also the property of a conductor, and the inductance is also the property of a conductor. Right now, we are focusing on the capacitance. We've already explained in detail that what is basically capacity means to us. Is there any measure of it? We say we do have a measure of it. So what's the measure of it? We say suppose you have a conductor, because it's a modified conductor basically. Suppose you have a conductor and you provide the charge to it. Let's say this is a conductor. This is a spherical conductor in the front of you, and you provide the charge to this. So as you provide the charge to this, what happens? The potential of this rises. So it's obvious that we can say that electric potential of this particular spherical conductor is directly dependent upon the charge, the amount of the charge. You increase the charge. How do you increase the charge? Give me a simple way out. Sir, you can increase the charge by increasing the size of this, of course. So you can have a bigger device, bigger size conductor, and you will have more charges on the surface. You have read this in the previous articles that on a conductor, the charge resides on the outer surface. So larger is supposed to be the size of this conductor, more will be the amount of the charges accumulated on it, and hence there will be a large potential associated with it. Now that's the potential. So what do? We remove the proportionality sign and introduce a constant term. That's 1 upon C over here. And that C over here is supposed to be taken as a capacitance. You can also write this particular relation in a convenient format that Q is supposed to be equal to C into V. Every constant has a deeper behavior. This constant over here introduces a capacitance, which is of course a property of a conductor, is also having a distinct behavior. The behavior has to be analyzed that is it really a constant, or you can modify it, or you can change its values as per your convenience. We say yes, we can. So on what factors does this C depends upon? The first factor on which it depends upon is supposed to be the shape and the size of the conductors. As just a few minutes back, I discussed about varied shapes and sizes of the conductors. or the capacitors like the spherical conductor or a cylindrical conductor. Very soon you will be learning about a parallel plate capacitor in which the plates are parallel, but they can be rectangular plates, they can be square plates, they can be circular plates. So it is going to depend upon the area of the plates. It is going to depend upon the separation between the plates. So we say the shape and the size of the conductors, and also the arrangement of the conductors. How do you physically arrange them? And then the languages are going to crop up. What kind of the languages? The concentric spheres, or the coaxial cylinders, or the plates which are placed parallel, and hence the parallel plate capacitors. Does it depend upon any other factor? See, the prime idea is for the storage of energy. And when it comes down to the storage of the energy in that condition, the energy has to be stored, not to be wasted. Wasted means what? You know that the electric field lines are originating from the surface of the conductor if the charge is supposed to be positive. So you can see these field lines over here. And where are these field lines? These field lines are moving in the region. No, they are not moving. That's a depiction. That's a spread of the field line. That's a spread of the energy. Repeating again, that's a spread of the energy. Where is this energy? From the surface to infinite, to infinity. That's the spread of the energy. Can you feel it? You can feel it. Are you in control of that energy? You generated that kind of energy, but are you in the control of that energy? No. How you can utilize the energy which is spread in the entire region? You can control the energy which is spread in a nearby region. That's what we want. And there comes the existence of the second plate, which we have to study in the article of the principle of the capacitor, which we will deal later. So the spread of the energy is a waste. But if the same energy is confined in a smaller region, let's assume that there is supposed to be another plate over here, like this, nearby, like this. So what will happen? Since it's a conducting plate, there will be the induction effects, and you will receive these negative charges at the nearby face of the conductor by the property of the induction. And then you must receive the positive charges on the outer side. But what we do, we play smart and we earth the outer surface, because of which the charges are now only on the interior of the outer conductor. What happens because of this? What happens because of this particular idea, that the field lines are now also able to terminate. Previously, they were not able to terminate, and they were moving to infinity. So you were not under control of the amount of the energy which you have generated by the idea. But now, as you can see in the diagram, the energy is getting limited. Energy is the same. So what do we mean by the limited? What we have done, we have increased the energy density. What's the energy density? That's energy stored per unit volume. The same amount of energy which was there was initially spread in the entire region, but now we are doing smart effects. We are having the same amount of energy, but we are storing this in the concise region. So basically enhancing the energy density. That's the meaning of the arrangement of the conductors. What are the features it depends upon? It depends upon the what kind of the medium is supposed to be there in between these plates, which is able to hold those charges effectively and hold that particular electrostatic potential energy in an efficient mannerism. So using that part, that's the third point, that it depends upon the dielectric medium between the conductors, or the plates, which we can say. So between the conducting plates. Does it depend upon any other factors? It depends upon the presence of the nearby conductors. As you can see in this article, supposedly previously it was supposed to be isolated. So the spread of the energy was large, but the energy was not useful. But with the presence of the second conductor, the capacity of this is enhanced. अभी तक हमने कोई formula नहीं बनाया, पर आपको एक आइडिया मिल गया है कि इस तरीके से आप एनर्जी के ज्यादा कंट्रोल में है, ज्यादा यूजफुल एनर्जी है, ज्यादा एनर्जी आपको दिख रही है, कम रीजन में कंट्रोल में है। जैसे आपके पास में कोई यूएसबी डिवाइसेस हो, या फिर आपके पास में कोई टेराबाइट की हार्ड डिस्क हो, उसके अंदर एनर्जी स्टोर हो जाए डेटा के फॉर्म में। So it's definitely going to depend upon the presence of the nearby conductors. So these are the 4 basic points on which the capacity depends upon. And you can quickly have a revision shot for it. That is the shape and the size of the conductors, arrangement of conductors, a dielectric medium between the conducting plates, and the presence of the nearby conductors. Now, what to do? We need to understand what are the steps for the calculation of the capacitance. So what are the steps for them? So let's quickly go through the steps. The step number 1, assume the charge Q on the plate of the capacitor. Now, which plate of the capacitor? We say the plate A of the capacitor. Let's say we have the 2 plates A and B, so we assume the charge Q on the plate A of the capacitor. So just structuring out a parallel plate capacitor in the front of you, as these are the plates of the parallel plate capacitor over here, and this side is earth head over here. So we assume the charge on this particular plate as Q over here. Let's assume this as a charge Q. So automatically, by the induction effects, the inner face of the second plate is going to acquire a negative charge. Does it seem like it is on the inner face? If it doesn't seem to you, then kindly show it. That these are the charges which are present on the inner faces over here. Right? So by the induction effects, this particular amount of charge which is present over here will be minus of Q. That's plus of Q there and minus of Q over there. So if I get a question that what is the net charge on the capacitor? What is the net charge on the capacitor? So that a net charge on the capacitor is supposed to be equal to 0. That's 0 plus of Q and minus of Q. So by default, when we talk about the charge on the capacitor, that we read as a charge on the positive plate of the capacitor. Once you are through with this idea, that is the charge which you gave, basically assumed on it, and then the induced charge on it. Why we are hell-bent on using the language assume? Reason because the capacity of a capacitor is independent of the amount of the charge present on it. Getting it or not? Repeating once again, suppose I have a glass which is having a capacity of 300 milliliter. That means the sizes of the 300 milliliter. What does it mean? It can hold 300 milliliter of the liquid. I pour in 300 milliliter of the liquid inside this. So what is the capacity of that glass? That's 300 milliliter. It is holding right now the 300 milliliter of the liquid, or let's say the water. Now what happens? I just take out the half of the fluid from it. So what is left? 150 milliliter of the liquid is left inside the glass. Now the student asks me, sir, explain what is the capacity of this particular glass? I say, my dear student, is still 300 milliliter. He said, why, sir? Because I say you can still add 150 milliliter more inside it. So the capacity is still 300 milliliter. Okay, sir, you empty the contents of it. So empty the contents of it. It's an empty glass now. So, sir, now is the capacity 0? No, the capacity is still 300 milliliter because you can add 300 milliliter of contents inside. What's the moral of the story? That the capacity of that particular glass does not depend upon the content. What was the content over there? That was a fluid. So on what feature does it depend upon? It only depends upon the size, the shape of that container. Are you getting the point or not? Of course you're getting the point. In the same mannerism, our capacitor is an arrangement or based upon the different structures, which are definitely going to depend upon the shape and size of the conductor, but it is independent of the content. Because the content is a charge. So the capacity of the capacitor is independent of the charge. Shall we write it in a note? Of course. So what's the note for this? That the capacity of a capacitor is independent of the charge on the plates of capacitor. So why do we study the charge then? The reason because the charge gives rise to the potential. So the potential of the capacitor, through which we are going to identify later on that what's a capacitor features are, is definitely going to depend upon the charge on it, but the capacity does not depend upon the charge on it. So we have to assume that charge. So we assume that particular charge on the plate, and then we check that the induced charges. Once you are done with this, the charge distribution, what you have done, we have analyzed the charge distribution. हमने तो सोचा था कि सिर्फ चार्ज क्यू दिया है, पर इंडक्शन की वजह से माइनस क्यू भी आ गया. So once you're through with this idea, what you're supposed to do in between the plates over here, at this particular point, in between the plates, you need to calculate the electric field lines. Not the calculation of electric field lines, the calculation of electric field intensity. As you can see that these will be the field lines which are present over here. And the presence of these field lines ensures there is a intensity of electric field. So calculate it. So calculate the electric field intensity in between the plates of capacitor. Very fine. Excellent. How do we find it is a question. That is by a technique. What is the name of the technique? Gauss law. So by using the Gauss law, if you are unable to use the Gauss law, then you go in for the integration techniques and calculate that particular electric field intensity over there. And once that is over, comes the next step, that is to calculate the potential difference via this electric field intensity by using the relation E is equal to minus of dV upon dr. That's using the potential gradient relation.